Foundations Pre-Cal 10, video number 7. So this is video number 3 in section 2. So we're talking today about slopes and rates of change, and you'll see the relationship between them here in just a minute. So here we go. Slopes, if you recall, slopes from grade 9, there's 4 types of line slopes, and generally read from left to right. So if we read from left to right, you can see here we start up and we finish down. So sometimes I like to think about your bank account. So if you start the day with money and you finish the day with less money and you didn't buy anything cool, that's not a great scenario. So that's a negative slope. So any line that has a up to down from left to right orientation is a negative slope, because the height is decreasing as the length is increasing. So then you can imagine this next one: as my length increases, my height increases. Those are both positive things. I'm moving in a positive direction and a positive direction. Here, like I said, I'm moving in a negative direction and a positive direction. There is a video on slopes from grade 9, section 7 as well, where I talk more about the direction, and we'll get into that a little bit more here. Remember that slope is also rise over run, right? This is again from grade 9. It is your change in height over your change in length. So when you see a slope like this, right, what's my rise? Well, I have a rise. Call it whatever you want, because the important part is, let's just say it's 7, right? Let's say that's 7 and that's 0, just for numbers. But what's my run here, right? My run is 0. I have no horizontal distance change. So what that means is I can't divide by 0. World explodes, universe ends, right? Heads explode. We can't do it. No, can't divide by 0. So it is undefined. A vertical line has an undefined slope. And then a horizontal line is similar, but vastly different in the fact that we don't have a rise, but we have whatever run we need. Again, I'll just plug some random values in there. Right? Because now what we get is 0 divided by anything is 0. So if you have a horizontal line, you have a 0 slope. If you have a vertical line, you have an undefined slope. And then you have your positive and negative examples. So those are the 4 different slope behaviors. So remember that slope is rise over run, and we can map it. So let's just say we had a line with a slope of 7 over 3. I'm just going to plug a random point on that. I'll say I know this point is on my line. Well, what it means is to get to the next point, go back to the white here for a sec, it's rise over run. And you can see both of these are positive, but it's important to understand that -7 over -3 is the same as 7 over 3. And you'll see the difference here in a second. Because if I'm going to map this one, I'm moving in a positive y direction, rise, and a positive run direction. So y and x, right? So I just count up 1, 2, 3, 4, 5, 6, 7, and I count positive 1, 2, 3. Now be aware, it doesn't mean positive as in the quadrant, but positive direction. Okay, a positive direction is to the right, a negative direction is to the left for the x values, and for y values, positive is up, negative is down. And then you could map that again. You could go 1, 2, 3, 4, 5, 6, 7, and then over 1, 2, 3. Next point exists there. Your slope is consistent. But now just for a sec, I want you to consider this one. Well, this just means direction of travel. You see, if I start at the top point I have there, I could count down 7, which is a negative direction, and then left 3, which is a negative direction. I could count down 7 and left 3. I could count down 7, right? So you can go either direction, so that relationship is important to grasp. So here we have 2 lines. Let's map their slopes. And you can see I've added little points right on these lines because you want to make sure you're at a perfect intersection. So let's just do some mapping here. So if we look at the first one, from this point here, we count down 1, 2, 3, 4. So -4. And then we count over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So you can see we have a slope of -4 rise over run. Now look, this could be simplified, right, to -2 over 9. So let's just see what happens if we only counted down 2. Well, we would be here, and then over 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can see there it is, another exact intersection. So that's how you map a slope. It's really straightforward. We're just counting from one point to the next. Sometimes we can find a point in between, sometimes not. So now let's look at the one on the right. Okay, I have a point here at -7, so I'm going to count up 1, 2, 3, 4, 5, 6. Then I'm going to count over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have a run of 10, a rise of 6, both positive. So I have 6 over 10, which again will simplify to 3 over 5. So I can double check that slope change. And you can see if I just went up 3, 1, 2, 3, and over 1, 2, 3, 4, 5, again, there I am on the line. So it works. Slope is consistent. Okay, so what if you have 2 points and we're not going to map it? Well, we have this equation, y2 minus y1 equals x2 minus x1. And all that means is you have 2 points. You have point x1, y1, and you have point x2, y2. The little 1 and the little 2 just signify point 1 and point 2, and you can pick either or. It does not make a difference. So let's just look here. If we were to pick this, and just label it for yourself. I'm going to call this point 1, and I'm going to call this point 2. Okay, which means I have, this is point 0, 3, and this is point 1, nope, sorry, not 1, 15, 16, 17, 18. So this is point 18, -1. So using the equation on the right there, the y2 minus y1, I'm going to take this as my point 2. So my y value of my second point is -1. I'm going to subtract the y value of my first point, 3. And then I'm going to put that over the x value of my second point minus the x value of my first point. And then I'm just going to do -1 minus 3, it's -4. 18 minus 0 is 18. And look, exact same slope, because it's the exact same line, right? This one here, but we've used it with an equation. So we don't always need to have the visual in front of us, because this is the difference in your height, and this is the difference in your length. And it doesn't matter which one is point 1 and which one is point 2, you would end up in the same place. So I'll just reverse them. So now what we'll do is we'll call this point 2 and we'll call this point 1, and you'll just see that what happens is, in the first one, my negative was in the numerator. But this time what I'll get is I'll get 3 minus -1 over 0 minus 18. So I get 4 over -18. So the slope is the same. It's still a negative slope, but my negative in this case is in the denominator. So it makes no difference which is which, as long as you're consistent. So let's jump over to the second one there. I'm going to call this point 1, has coordinates of 0, -7. And I quickly shifted to blue. Didn't mean to do that, but not the end of the world. It's live video for you here. And then 10, -1. This is my point 2. So I'm going to go -1 minus -7 over 10 minus 0. So again, now I'm going to get 6 over 10, which is 3 over 5, which again is exactly the same as what we got here by mapping. So you can get it either way. You can map it or you can just calculate it. If you don't have the graph in front of you, know that you can just calculate it. Now, here I talked about it on that first page, but slopes of vertical and horizontal. So here we have a point and a point, and you can tell there's no rise and no run, but let's actually do it using the point formula. So this is -4, 5, and this is 4, 5. So if we threw this into that y2 minus y1 over x2 minus x1, we would get 5 minus 5 over 4 minus -4, which gives me 0 over 8. And that's why I have a slope of 0. And you can see in this example, we have points again. We have 5, 1, and we have 5, 5. If I plug that into the equation, this time I'm going to get 5 minus 1, and I'll let you can see which one I'm using is point 1 and point 2, and then 5 minus 5. So in this case, we end up with 4 over 0, which is a big no-no. We can't divide by 0, and that's why you have an undefined slope for a vertical line. So what about slope as a rate of change? Now, we've seen this before. In fact, you interact with it every day, because all it is you add units to a slope. And we talked about independent and dependent variables in previous videos, but just think you could map relationships between day-to-day occurrences on a graph. And I'll give you a few examples as units here. Kilometers per hour. There's a slope. It's a certain number of kilometers for a certain number of hours. What about dollars per hour, right? There's your hourly wage. It has a slope. It's a linear equation, right? There are more. Just to consider your fuel consumption of your car, right? You burn kilometers per liter. So how far you can go depending on how much fuel you have in the car. So it's all same as a slope, but we've incorporated units into it. So we call it a rate of change. When you get really higher level calculus, for instance, imagine a big container like this and you were filling it with water, right? The water that goes in creates a volume, and we'll say meters cubed, and the length of the container is just a distance in meters. So you can have a rate of change that says the volume meters cubed with respect to the length of the container per meter. Now people might think, oh, let's simplify that to meters squared, but no, you can't do that because this is a rate of change. For every increase in the length, there is an increase in the volume. For every increase in time, there is an increase in kilometer, right? So all of these things are related rates. So here's a couple examples. So Paul rents a car with a full gas tank. I know everyone loves word problems. The odometer reads 86,347 kilometers. Paul used the car for 3 days. When he rented it, the odometer read 86,721 kilometers, and it needed 63 liters to fill up. So there's lots in here. The cost of the car was $96, and then gas, which was 90 cents per liter. So we're going to look at a whole bunch of different rates here. So it's important to consider the units that you're looking for. So if you look at determine the rate of gas consumption of the car, well, that means we're looking for units of kilometers per liter. We want to know how far we can go with the gas. So it means we need to come up with two sets of points here. Remember, this is my y value, and this is my x value because it's rise over run, right? Slope is rise over run. So I'm looking for 2 points that are liters and kilometers. So look at the info we have. It took 63 liters to fill up, which means if we start liters as my x value at 0 and we finish at 63, that just shows a rate of change of how much you have to fill. So let's say if you're at 0, you're empty, it takes 63 to fill it full. But the relationship here is going to be, if 0 is where I start, then where did I start for my distance? I started at 86,347. And where did I finish with my distance? At 86,721. So I've set myself up a set of ordered pairs that give me liters and kilometers, and they're in the right spot. They're in the x and the y. So I just set up that equation like we did for slope, and I go 86,721 minus 86,347, I missed a 3 in there, over 63 minus 0, which gives me 86,721 minus 86,347. I get 374 over 63. Now here's where the units are important. This is kilometers per liter. But this isn't per liter right now. This is per 63 liters. And I want per 1 liter. So all we have to do is divide. 376 divided by 63 is 5.94. We'll round there. Kilometers per liter. So that is the rate of gas consumption in the vehicle. You can get 5.94 kilometers per liter. So now part B, determine the average rate of travel. So now we're looking for distance per day, right? So our new units, I'll do it in yellow, our new units we're looking for B is kilometers per day. So we're setting up a new set of points. So we're not going to use points that look like that anymore. But again, remember your day is on the bottom, so your day is your x value. And pretty sure we can say we start at 0 days if we're going on a trip. And in this case, we finish at 3 days. And now the kilometer value is the same because we're still looking for how far did we travel. So we need our starting distance and we need our finishing distance. So the calculation we did here is going to stay the same. The only difference is on the bottom, we're going to have 3 minus 0. So the difference here will be 374 divided by 3. And again, that's kilometers per 3 days. I don't want 3 days. The units tell the story. I want 1 day. So 374 divided by 3. We go 124.7 rounded there kilometers per day. So it's all about the units, and you're going to see units, units, units. If you're doing workplace 10 or workplace 11 eventually, or you go into trades, or really anything you deal with, because eventually when you start dealing real world applications, you have units. The units will tell you the story, and they help you determine whether or not you've done the calculation correct. So now the last one is determine the cost of renting the car per day. Well, there's a few things happening here. One, the cost of the rental car up front was $96. So that's going to be a little bonus over here, right? We'll deal with that in a minute. If it's $96 for the whole trip and the trip was 3 days long, that means you're already going to be at a price of $32 per day, right? But you pay 90 cents per liter. So how many liters did we burn through? We burned through 63 liters, right? So we burned through 63 liters. You can look at this a number of ways. 63 liters per day then, right, because that's per 3 days, is going to give us 21 divided by 3. We went through 7 liters per day. And how much is gas? Well, it's 90 cents per liter. So 90 cents per 1 liter, and watch the units here, times 7 liters. You can see liters cancel with liters, so we're left with a dollar value. So 0.9 times 7, it's $6.30 in gas per day. So it costs us that, and it cost us that per day. So we add them up together, and we get the daily rate is going to be $38.30. A lot going on here, but we'll do this example in class as well. But it's all about the units and how you can make the questions make sense for you. So here's a couple examples of how to graph a rate of change. And the scale of your axes is really important. You can see here I have my axes not labeled yet, but look at the info you have. We have years, so this is going to be time in years, and then we have money, so this is going to be dollars. And you can see the scale of my units go up here. This is 500, 1500, 2500, right? It's always important to look at your scale, and this is by year. So 1, 2, 3, 4, 5. Now, what information do we have? We have, and remember, look at your axes here. X is time. So it means in the year 2000, the TV was $4,600. We have a point there. And in the year 2010, the TV was worth $1,200. So what does this look like on my graph? Well, in 2010, I was at $1,200. So find 2010. So 1, 2, 3, 4, 5, 6, 7, 8, 9. It's right at the edge of the screen of the graph. Price was about $1,200. So if this is 15, this is $1,250. So we're a little bit below that. So we got a point about there. And then in the year 2000, it was $4,600. So if this was 45, then 46 is just a little bit above, so about there. And the rate of change is consistent. So there's your graph, right? A vertical line. That is the graphical representation of the decrease in price of the TV. Now, how do we get the drop in price per year? Remember, these have units. This is year, and this is price. And we have y2 minus y1 over x2 minus x1. So we get 4,600 minus 1,200 over, now you got to be careful here with the years, 2010 minus 2,000. Sorry, not in this case. There are sometimes you need to be careful with years. And we might see an example of that in a minute. So 4,600 minus 1,200 gives us 3,400 over 10. Which simplifies to 340 per 1 year. So what is the price drop? Remember, it is a drop, so it is negative 3,400, which means, 340, which means I set up this equation, got myself all caught up, 4,600 minus 12, and we are actually going 2,000, there we go, set that up backwards, 2,000, right, got to keep your x1s and x2s consistent over 2010, which gives us negative 10, which gives us negative 340. How did I know that was the case? because you can see that this is a negative slope and it is a depreciation rate. So careful there. Everyone makes mistakes, even me. So let's do one more here. So here's another depreciation. So most cars depreciate as they age. Car costs $30,000 when you bought it. So this is tough to demonstrate on the graph, but 30,000 is right at the very top corner because that's 0 for time. Again, we have time down here and we have money here. And then it has a value of 2,500 after 10 years. So all the way over to 10, and we find, you see the scale here is 3,000, which means that's 1,500. So 2,500 will be a little bit above there. So graphically, that's going to see how our car depreciates in value. Now, a whole other discussion about depreciation versus appreciation, but we'll do that at a later date. So here is the graph there. Now, write a formula for the value when it is t years old. So in this case, my slope is my depreciation value. So what's my slope here? Well, I have points 0, 30,000, and I have a point 10, 2,500. So to get my slope, I do my slope equation. So 2,500 minus 30,000 over 10 minus 0 gets me negative 27,500 over 10, which gives me negative 2,750 per year. So there's my slope. So my value is equal to my slope times however many years it's depreciated plus my y-intercept, 30,000. We'll talk more about this in class, but you can create equations of straight lines. And I think we have one more here, but there's a lot going on in this question. So this should be A and B, not C and D, formatting. So determine the car's value after 4.5 years. Oh no, sorry, it is C and D, because go back here, that was A and B. So now we're going to use this equation to determine some information from it. So we had value equals negative 2750 times t plus 30,000. So determine the car's value after 4.5 years. Forget graphically, we can do it mathematically. We plug in, so value equals negative 2750 times 4.5 years. So that's the depreciation rate per year times 4.5 years plus 30,000. And if we solve that equation, we get 17,625. So it means after 4.5 years, we're at about 17,600. And if we do go back to the graph, 4 years tracks to about here, which is, oh, sorry, we should be at 4.5. Let's just fix that. I was like, that's not going to work. 4.5 is about here. So just below 18,000. So the graph demonstrates our calculation. So when is the car's value between 12,000 and 15,000? Well, there we can go back to the graph. Where is it in between 12,000 and 15,000? So here's 12,000 and here's 15,000. So we are in between. Graphically, we can look at about 5.5 years and 6.5 years. Now you can throw that into a calculation as your value. I'm not going to do it here, but I'll let you do some of the legwork. We can throw it in as the value. So what you would do is you would go, okay, 15,000 equals negative 2750 times t plus 30 grand. And you're doing some algebra to solve for t. I mean, hey, let's do this one. So subtract 30 grand from both sides. And then divide both sides by negative 2750. So we have negative 15,000 divided by negative 2750, and you get t equals 5.45. You do that again for 12,000, and you'll probably get t equals about 6 point. And that's how we can come up with the mathematical relationship. So a couple more here. How much value does the car lose every 2.5 years? So in this case, you're taking your value and you can plug in any value amount you want. But if we start with the value being full, so time equals 0, right? We have a value of 30,000. So When t equals 0, we have a value of 30,000. Okay, well, what about when t equals 2.5? So that just means we go value equals negative 2750 times 2.5 plus 30,000, and we'll get the value after 2.5 years. So negative 2750 times 2.5 plus 30,000, and we get 23,125. Subtract that from 30,000, and we will get $6,875, and that's how much it loses per year. And then what is the rate of change in the car's value with respect to time? Well, that is just our slope. It is negative 2750 per year. So you can see how rate of change relates to slope. It's connected to our section 2.3 in the notes. This is a long video, but definitely worth a watch because rate of change is going to come back again and again and again. Great work. Keep on going. You're doing awesome.